Section 7.11 is called Further Aspects of Sources and Loads. So we've got this basic understanding of three types of power, right? We're talking about apparent, reactive, and active power. So what can we do with that information? Okay, so we're taking this idea of this reactive power, and we're told that it exists, and that was new for us. And we're told also that this reactive power, certain loads can be considered active or reactive loads. They can be considered active or reactive sources, and so forth and so on. So let's take this a little bit further, and let's look at a very simple real world application of this knowledge that we have. And it involves a very simple passive device that we've studied and looked at before, namely a capacitor. All right, so what we're looking at here, it looks very similar to other circuits that we've used. The only difference really here in, say, figure 710 that he references, this guy was that there was an inductor there, which he sometimes calls a reactor, right? But here, what we've done is we've replaced the inductor with a capacitor. And everything else, we gotta sort of get a perspective on this. Here's our AC source providing a voltage, and this resistive element is in parallel with that source, and this capacitive element is also parallel with that source. So the what we're going to see, or what we're going to explore here, is that reactive power is going to flow from the capacitor, and that's indicated here with this Q flowing back to the source. Reactive power is going to flow from the capacitor to the source, while active power is going to flow from the source to the resistor. And they're going to actually, here's two powers, and they're actually flowing in opposite directions over the same transmission lines. Okay, again, this is not theoretical. This is not, some abstract idea here. This is what really goes on. And, so this is what we're looking at in this case. And like he says here in the textbook, if we had this watt meter connected to this circuit here, then we would get a positive reading of power in watts, right? And then what we would also get is from the VAR meter here, we would get a negative reading indicating with the VAR meter that the reactive power is actually flowing in the opposite direction as it would from an inductor. And that means that it is delivering reactive power back to the source. Okay, so the source itself, if we look at everything in terms of the source here, this source is sort of pulling double duty, isn't it? It's a source of active power. Okay, and it delivers active power, but it also receives reactive power. So it's an active source and a reactive load simultaneously. Now, again, that's a sort of a strange thing for us, as we first start to interact with this. And it seems unusual that we would have two powers flowing in opposite directions. But again, we have to remember that active power is not the same as reactive power, and that each flows independently of each other. And also, like we were told earlier, you can't convert one to the other. And then he goes on to take this a step further, and he says, when you talk about sources and load, even a basic 120 volt AC receptacle that we have in our homes are ultimately connected to some huge alternator somewhere that powers the electrical transmission and distribution systems. And odd as it may seem, an electrical outlet can act as both an active and reactive source, as we would expect, but it can also behave as an active or reactive load. Up to this point, we always think about the receptacle as, pushing or providing, right, this electrical energy to us. But, it can also behave as an active or reactive load as well. And what makes it function that way? Well, it depends upon the type of device that's connected to the receptacle. Okay? And if that device absorbs active power, the receptacle will provide it. If the device delivers active power, the receptacle will receive it. So in other words, a receptacle outlet is at all times ready to deliver or accept either active or reactive power based on the things that are connected to it. Now we can take this, to another level, and we could say those same ideas apply to a three-phase 480-volt service entry to a factory, or to the terminals of a high-power 340,000 kilovolt transmission line. Okay, so what I've done here, and this is example 7.9 that goes along with section 7.11, and he says, suppose that we put a 50 microfarad capacitor across the motor terminals of example 7.8. Example 7.8, it was a problem that represented the motor as a, you had a resistive and an inductive component of that. And so, if you look back at that, you can see that circuit in example 7.8 looked like this guy, okay, with this part of it. So all I've done here, and all we're going to do in this example, is we're going to add a capacitor to it. Now, at the same time, with that problem, we came up with this representation in terms of the power triangle, as specific to this problem. All right, this problem, excuse me, this problem. These were the results of that. There's the reactive, there's the active, and apparent power. Simply by placing a capacitor in parallel with that same circuit, we can cause the whole of the characteristics to change. And we're going to walk through this very important example, 7.9. And here's the 50 microfarad capacitor. And he says, what is the reactive power generated by the capacitor? Notice the terminology. The capacitor is a source of reactive power. What is the reactive power generated by it? Well, first off, I have to determine what the impedance of that capacitor is. And so for part A of this problem, I need to define capacitive reactance as 1 over 2 pi f times C. I'm given the value of the frequency as 60. So this is 1 over 2 pi times 60 times 50 microfarad. Taking the value of that, taking the inverse of that, I end up with a value of 53 ohms of impedance, capacitive reactance, impedance of 53 ohms. Now, if I know, as before, that that's a 120 volt source and that's 53 ohms, to get the current that that we're looking for in that particular problem, then all I have to do is take 120 volts, divide it by 53, and I come up with 2.26 amps that are flowing in that branch where the capacitor is. Now, all the other values, they haven't changed, right? This is still, 390 watts, and this is still the 456, VAR here. So none of that part of it's changed because all these components are connected in parallel. So they're all seeing the same thing that they saw prior. to us making this simple modification with this capacitor. And before we go into the next thing, this is something you actually do in a circuit to improve the power factor. And it's fundamentally called power factor correction. And let's walk it on through. Part B says, what is the active power of the motor? Well, it's the same as before. The active power of the motor remains 390 watts. The motor also draws the same amount of reactive power before from the inductor of 456 VAR, right? So that's still going on just like before because of the parallel connection. Now, the motor draws 456 from the line, but the capacitor at the same time is providing 271 VAR. Okay, now did I put that in there? No, I didn't, excuse me. So to quantify this, that power that is being provided by the capacitor is going to be that current there, times the voltage, and that comes out to be a value of, we already said that once, 271 VAR. So here is this system. The motor is drawing the 456 VAR for the magnetic field in the inductor. At the same time, the capacitor is furnishing 271 VAR. So the net reactive Hughes of L, we'll call it, is 456 minus 271 for a net of 185. Okay. The active power remains the same. Piece of L is still 390 watts. Now, what we can do with this, we can go back and look at our original power triangle, which was this, right? I'm going to outline it for us. The original power triangle with this problem was the green here. Okay, it was all of this. You know, here's our 600. You know, here is our 390, and here was our 456. Now, by the addition of the capacitor to this, it causes the reactive power, net reactive power, to go down. It goes down to this new level here. All right, so I'm 456 minus 271. Okay, for that, for a new net value of reactive of 185. All right, now, this angle here, which if we take the cosine or the inverse cosine of this value, we're going to find out what the power factor is for that. And we're going to see that we have improved the power factor. Initially, it was at 65%, but I'm a little ahead of myself. Let's find out what the new apparent power is, which is part D of this. S, apparent power, is going to be the power, active power squared, okay, plus the reactive power squared, the net. So that's still 390 squared plus this 185 squared. Square root of all that comes out to be 432 volt amps. All right, now look, this apparent power has moved from this value, now it's down to this value, simply by adding a capacitor to that circuit. Now, I can also, since I have this new system here, I can recalculate the total current. Initially, it was 5 amps. Well, now it's going to be different than that. The total current that is drawn now is going to be the apparent power divided by the voltage will give us the current, and that is going to be the 432 volt amps divided by the voltage, everything's still in parallel, and that comes out to be 3.6 amps. All right, now think about that. Simply adding a 50 microfarad capacitor to that circuit, which we did here, nothing else changed. We lowered the total current from 5 amps to 3.6 amps. That's a big improvement. And the line current is much smaller. There's a lot of considerations for that. You know, in a large system, if we can lower the overall current, we might could use a smaller conductor, right? Because it's not needing to draw the same amount of current. There's all sorts of additional benefits of that going on. I can calculate my new power factor of the line, you know, to where, you know, the cosine of the angle that's given is going to be the active over the reactive, active over the apparent P over S, and that comes out to be 0.903 or 90.3%. And that if I take the arc cosine or inverse cosine of that 0.903, we get this new angle of 25.5 degrees. Whereas initially, I don't know if we had that down anywhere. Did we have that down somewhere? Yeah. And then, you know, before that, you know, we had a different angle. I'm not sure that's associated with that. Never mind. I don't know that we calculated the angle before, but anyway, as that angle gets smaller, right, it's going to get closer and closer to 1. So, you know, if you take the you know, what's the cosine of 0 degrees, for instance? So anyway, you know, so we have lowered this angle from this value to this new value here, right? This angle. We've improved the power factor of the line. And so, you know, the reactive power generated by the capacitor, you know, we always want to draw that downward, you know, so it's decreasing the total. And we compare that to the power triangle of figure 712, which is what we've been doing all along here. We can visually observe the effect on that capacitor in the circuit. This is a thing that you do in motor installations. You put a capacitor in parallel with the motor, usually close to the motor, and what that will do is improve the power factor. Improving the power factor lowers the overall current because simply you're providing less current for less reactive power. All right, great section, very important. Make sure that you understand what we did there. And that's sort of a practical application of why you do what's called power factor correction.